Assalamu alaikum dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 22nd lecture of Thermodynamics 2. Lecture 22. The contents of lecture 22 are Exergy of an open system, second law efficiencies, relation of second law efficiency, numerical problems, and conceptual question and answer. Exergy of an open system. So we will drive a relation for exergy for an open system. So in the previous lecture, we have already derived the relation for exergy for a closed system. So in the closed system, we have derived a relation for piston cylinder system. And now in the current lecture, we will derive a relation for exergy for an open system. So in the right hand side, you are saying for open system it's the flow process. So a control volume is shown here. So inlet properties of a control volume is shown on the left hand side, and the outlet properties of control system are mentioned on the right hand side. And an open system is a system in which there is a continuous flow of fluid or working fluid between the boundaries of the system. So this is a control volume. The mass that is at the inlet is m in. C1 is the velocity of the fluid at the inlet. T1 is the temperature of fluid at the inlet. H1 is the enthalpy of a fluid at the inlet. And that fluid will enter into the control volume and leave out with the mass m out. So m out is the mass at the exit, C2 is the velocity of a fluid at the exit, T2 is the temperature of fluid at the exit, H2 is the enthalpy of a fluid at the exit. And Z1 and Z2 are the elevation, so that is the mean elevation with the inlet and mean elevation at the outlet. So Z1 is the height at the inlet and Z2 represent the mean height or mean elevation at the exit. So to find out a relation for an exergy for an open system, we will use the energy balance equation. So here we have used the energy balance equation. So energy at the inlet is equal to energy at the outlet, and we will apply the steady flow energy equation for this process. So Q plus H1 plus C1 square by 2 plus GC1 is equal to W plus H2 plus C2 square by 2 plus GC2. So we have already derived that relation in the previous lectures as well. If you forget, you can go back and revise that derivation as well. So we have steady flow energy for two different units. So for the small q, the unit of the steady flow energy equation is kilojoule per kg, and when that equation is multiplied with the mass flow rate on both sides, the units of the equation is kilowatts or kilojoule per seconds. So in the third step, the mass flow rate is multiplied on the both hand side, and the small q is now the capital Q, and the capital Q unit is kilowatts. So it's the mass flow rate into the inlet enthalpy plus mass flow rate into the kinetic energy component at the inlet plus mass flow rate into the potential energy component that is at the inlet plus work W is the amount of work that is taken out or input in the system, mass flow rate into the enthalpy at the exit, that is H2, mass flow rate into the kinetic energy component at the exit, plus mass flow rate into the potential energy component at the exit. And the entire unit for this equation are in kilojoule per second or kilowatts. Joule per second is the watt, so either it's kilojoule per second or kilowatts. Now W is the amount of work done, useful work done, so that is equal to exergy or available energy. So we take the W term on the one left hand side and all other parameters on the other side of equation. And taking the similar term common, we have mass flow rate into change in the enthalpy plus mass flow rate change in the kinetic energy component plus mass flow rate and to change in the potential energy component plus Q is the amount of heat that is transferred from surrounding to the system. Now in the previous slide we have utilized the energy balance equation and we have approached to a certain relation. Now we will use the entropy balance equation. Because the heat is transferring into the system and there is a mass flow rate, so you know that for entropy transfer mechanism it includes the mass transfer as well as heat transfer. So for entropy balance equation we have Q over T naught plus m dot S1 plus S gen, that is due to the irreversibility, plus m dot S2, that is the entropy at the exit. So entropy due to heat transfer is Q by T naught. Due to mass transfer is m dot S1. Due to irreversibility, that is S gen, m dot S2 is the entropy at the exit. For here we are assuming that the process is reversible, so we are cancelling the term S gen out. So the relation for Q from the entropy balance is equal to Q is equal to m dot S2 minus S1, that is the change of entropy between state 2 and 1, into T naught, that is the temperature of ambient. So here from with the help of entropy balance equation we have calculated the value of Q, that is heat transfer. So we will insert the value of Q from the entropy balance equation into the energy balance equation. So that is the relation that we have obtained in the last slide. So here we have a value of Q. We will replace the value of Q with the value of Q that we have obtained through the entropy balance equation. So the value of Q, that is m dot S2 minus S1 into T naught, is placed in this relation, and we will take the subscript that has 1 on the in the first bracket and the term that contains the subscript 2 or the properties of state 2 in the one bracket and properties of state 1 in the separate bracket. So here we have W is equal to m dot into H1 plus kinetic and potential energy component at the inlet minus T naught S1 minus m dot enthalpy at the exit, kinetic and potential energy component at the exit, minus T naught S2. So this relation represents the change in the available energy. So at the inlet you have the maximum available energy. So as this working fluid passes through the control volume, there is certain amount of available energy that is lost. So to calculate the change in the available energy due to this process, you may utilize this relation. So this relation will be used in the numerical as well. So the change in the available energy or the maximum work or exergy can be calculated with the help of this relation. So we have already discussed about the availability function when we were discussing about the exergy for closed system. So similarly as in the closed system, the availability function is phi, and in the open system it is psi. So the availability function for open system is represented with the simple symbol psi. So this is the same schematic diagram for the open system. Inlet properties are on the left hand side, outlet properties are on the right hand side. The ambient temperature is T naught. So dead state temperature and the heat content of dead state are T naught and Q naught. That is the ambient temperature T naught, and Z1 Z2 are the elevation at the inlet and outlet respectively. So in the previous slide we have derived the relation for the change in the available energy. So that available energy between the inlet and outlet, there will be a change in the available energy. To calculate the available energy for open system, we will utilize the relation that was obtained on the previous slide. Now we want to convert that relation in terms of availability function. So the availability function for open system is represented with the symbol psi. So psi is equal to enthalpy plus kinetic energy component plus potential energy component into T naught S. So for psi 1, that represent the availability function for the inlet, and psi 2 represent the availability function for the outlet. So psi 1 is equal to h1 plus c1 square by 2 plus gc1 minus t naught s1, whereas psi 2 that represent the availability function for open system for state 2 is equal to h1 plus c1 square by 2 plus gc2 plus t naught s2. So the relation uh, the relation, the last slide, the relation on the previous slide to calculate the change of available energy is quite lengthy. So to reduce it, we will use the availability function for open system, and that represent the change in the availability, loss in the available energy in terms of availability function. So if you are asked to calculate the change in available energy or loss in available energy in terms of availability function in the numerical, then you will use that relation as well. So you will write this relation, then individually you will calculate the value of availability function at the inlet and outlet, and the difference of that availability function will tell you the change in the available energy value. So We have already discussed about the dead state in the previous lecture as well. So the availability function for the dead state is represented with the subscript 0. So that is the availability function for open system, that is psi naught. So psi naught represent the availability function for the dead state. To calculate the exergy for the inlet section, so as we have discussed, the symbol capital X represent the exergy value. So to calculate the value for exergy at the inlet, we will use the relation of X inlet is equal to psi 1 minus psi naught. Psi 1 is the value of availability function at the inlet. So availability function value at the inlet minus dead state availability is equal to exergy for inlet section. And similarly, to calculate the exergy value for the outlet section, we will utilize the relation x out is equal to psi 2 minus psi naught. Psi 2 is the value of availability function at the outlet, and psi naught, similar to in the above equation, psi naught is the availability function value for the dead state. So the difference will tell the exergy value at the outlet section. So here we have a special case of availability function that is known as Keenan function. So what is Keenan function? So when the change in kinetic and potential energy are negligible, then this becomes a special case and change in exergy is represented by Keenan function. So in thermodynamics, Keenan function is the change of exergy for an open system for a special case when there is no change in the potential and kinetic energy component at the inlet and outlet. So for example, here we are given a control volume setup, schematic diagram of a controlled volume. Inlet properties are shown on the left hand side. On the right hand side, properties at the exit are mentioned, and the kinetic energy component contains the velocities term. So the C1 and C2 are the velocities at the inlet and outlet. So to for the special case for kinetic energy components are negligible, change in kinetic energy component is negligible. So C1 is equal to C2. For C1 equal to C2, there will be no change in the kinetic energy component. And similarly, Z1 and Z2 represent the potential energy component. So for Z1 equals to Z2, there will be no change in the potential energy component. So both height or elevation become equal. So the potential energy component are same and there will be no change in the potential energy component. So it becomes a special case for exergy for open system. So then this special case of change of exergy or available energy is represented with the Keenan function. So Keenan function is represented with the symbol of beta 1 beta. So beta is what is beta? Beta is equal to h plus t naught s1. So here you can see that the kinetic and potential energy function are ignored and component are neglected in this relation. So here beta is equal to, or Keenan function is equal to enthalpy minus T naught is the dead state temperature and S1 is the entropy at the inlet. So exergy in term of Keenan function can be written as H1 minus T naught S1 minus H2 minus T naught S2. So in term of linear function, exergy is equal to beta 1 minus beta 2. So here is a new topic, that is second law efficiencies. So mostly that topic is usually discussed in the chapter of Exergy. So here we will discuss this topic. So we will discuss what is meant by second law efficiency and why it is necessary to find second law efficiency. So second law efficiency is a measure of how much of theoretical maximum Carnot efficiency you can achieve, or in other words, a comparison of the system thermal efficiency to the maximum possible efficiency. So you know that the Carnot cycle we have already discussed, the cyclic heat engine. So we have discussed the Carnot cycle. So we know that the Carnot cycle is based on 4 reversible processes, and the maximum thermal efficiency that can be achieved by any reversible heat engine can never be greater than the Carnot efficiency. So the value of Carnot heat cycle efficiency or thermal efficiency of Carnot heat engine is maximum. So for practical heat engine, the value of efficiency will always be less than the Carnot heat engine efficiency. So second law is a measure how much the efficiency of the heat engine that is proposed or that is in the discussion has the corresponding, we have a comparison between what is the efficiency of that heat engine that is under discussion and comparison with the Carnot heat engine efficiency. So the second law efficiency will always be between the Carnot and first law efficiency. So in time we will discuss what is first law efficiency and what is Carnot efficiency and how we will calculate second law efficiency. So here is a relation to find the second law efficiency. So eta and second, 2i capital I or thermal efficiency of second, ठीक है. So to represent or to find how second law efficiency is calculated, so here is the relation. So second law efficiency is equal to actual thermal efficiency divided by maximum thermal efficiency. So actual efficiency is W actual divided by Q in. So here we have a practical heat engine. So in a numerator its actual efficiency is calculated, whereas in the denominator it is multiplied by the efficiency of Carnot heat engine. So because maximum efficiency or thermal efficiency maximum is can only be achieved by Carnot heat engine, so it is a ratio. Second law efficiency is the ratio between the efficiency of actual heat engine divided by maximum thermal efficiency. So actual efficiency is calculated by W actual divided by Qn, and thermal efficiency maximum or Carnot heat engine efficiency is calculated by W max divided by Qn. So Qn will be cancelled out and the term left is second law efficiency is equal to W actual divided by W max. So maximum work is obtained by only reversible heat engine, therefore W max is changed with WREV, that represent work output of a reversible heat engine. So this relation is for work producing device, and on the right hand side we have another second law efficiency relation for work consuming device. So let's suppose if we are discussing about heat engine and we have to find the second law efficiency of any heat engine, then we will use that relation on the left hand side that are in blue color, or and on the right hand side the color of the relation or equation are purple. So for work consuming devices like we are discussing about refrigerator, heat pumps, then we will be using the relation that are on the right hand side that are in purple color. So here we have W reversible on the numerator side and W actual in the denominator. So for work producing, W actual is in the numerator and W reversible is in the denominator, whereas for work consuming device, W reversible is in the numerator and W actual is in the denominator. So these are opposite. Similarly, if we are if we have coefficient of performance, so we will have coefficient of performance of actual device on the numerator and coefficient of performance of reversible device or corner refrigerator we have in the denominator, coefficient of performance of reversible device in the denominator. So here we have a example problem. So we have in the two different schematic diagrams we have shown two heat engines. So here on the left hand side it is heat engine A, and on the right hand side we have heat engine B. So first we will discuss how heat engine A is constructed. So the source temperature for heat engine A is 600 Kelvin and the sink temperature for the heat engine A is 300 Kelvin. And work output of heat engine A is 30 kilojoules. So the heat that is absorbed by heat engine A from source is 100 kilojoules, and heat that is rejected by heat engine A is 70 kilojoules. And for heat engine B, the source temperature is 1000. So for heat engine A it was 600, and for heat engine B the source temperature is 1000 Kelvin. The same amount of heat, 100 kilojoule, is absorbed from source into heat engine B, and 30 kilojoule of work is produced by heat engine B, and 70 kilojoule, that is same amount for B and A, has same amount of heat that is rejected into the sink, that is also at 300 Kelvin. So you can see, compare that only the source temperature of heat engine A is less than heat engine B, whereas all other parameters are same. Look at, you see that QH of 1 is 100 kilojoules and QHB is also 100 kilojoule, QLA is 70 kilojoule and QLB is 70 kilojoule, and WA and WB are also equal 30 kilojoules for both, and only difference is the source temperature. So now we will know, after solving this example, we will be able to comprehend why the second law efficiency is important. So you should remember that the properties of heat engine A and B are all similar, except that the source temperature of heat engine A is less and heat engine B is greater. So when we are calculating the thermal efficiency of heat engine A in accordance with the first law of thermodynamics, then the efficiency comes out to be 30%. So efficiency is W over Q. So 30 over 100, that is 30%. And on the right hand side, we are calculating the thermal efficiency of heat engine B in accordance with the first law of thermodynamics. So similar, Q thermal efficiency is W by Q, 30 by 100. So thermal efficiency of heat engine B is also 30% for in accordance with the first law of thermodynamics. Note, we cannot check the performance of any engine based only on the first law of thermodynamics. We must check the performance in accordance with the second law of thermodynamics as well. So in the previous slide we have two different heat engine, but they have similar parameters. So QH and QL and W work output for both engine was same, but the source temperature were different. So heat engine A has less source temperature and heat engine B has greater source temperature. But when we have checked the thermal efficiency based on first law of thermodynamics, that is same for both heat engines. Now we will check the thermal efficiency according to the second law of thermodynamics. So what is the procedure? So from second law of thermodynamics, the maximum efficiency. So if we have changed or replaced with the heat engine A is replaced by a reversible heat engine, then it has the maximum efficiency. So let's suppose heat engine A is a reversible heat engine, then it will have maximum efficiency. So to calculate the efficiency of reversible device, the formula is 1 minus T 2A over T1A or TL over TH. So maximum efficiency for heat engine A is 50%. So when we were calculating the thermal efficiency according to the first law of thermodynamics, it came out to be 30%. But when we are calculating thermal efficiency according to second law of thermodynamics and considering that the heat engine is a reversible heat engine, then the efficiency comes out to be 50%. Now how to calculate second law of efficiency? To calculate second law efficiency, we will be dividing the actual thermal efficiency with the maximum thermal efficiency that can be achieved. So we will divide 30 by 50. So the thermal efficiency comes out to be 60%. So 30% is the thermal efficiency that we have calculated according to first law of thermodynamics, and 50% is the thermal efficiency that we have calculated according to second law of thermodynamics and considering that the heat engine is a reversible heat engine. And then we have taken the ratio of actual efficiency with respect to the maximum thermal efficiency. So second law efficiency for heat engine A is 60%. Now we will be calculating the second law efficiency for heat engine B. So eta max B. So now we are considering that we have replaced the heat engine B with a reversible heat engine. So the relation to find the efficiency for the reversible heat engine is 1 minus TL over TH. So here TH is 1000, and for heat engine E the temperature of source is 600, and in heat engine B the temperature of source is 1000. So maximum reversible thermal efficiency for the reversible engine is 70%. So here that's how we have calculated. So now to calculate the second law efficiency for heat engine B, we have the relation efficiency of B divided by maximum efficiency of B. So 30 is the amount, 30% is the thermal efficiency that we have calculated according to first law of thermodynamics, and 70 is the value of percentage efficiency that we have calculated according to second law of thermodynamics, and considering that heat engine B is a reversible heat engine. So to calculate second law efficiency for heat engine B, we will take the ratio of actual efficiency and maximum efficiency. So second law efficiency for heat engine B is 42%. So now you know that second law efficiency tells the difference. So for heat engine A it is 60% and for heat engine B it is 42%. So second law efficiency is very important because it also incorporates the source and sink temperature as well. So in heat engine A it is producing the same amount of work whereas the source temperature is 600 Kelvin, and heat engine B is producing the same amount of work whereas the source temperature is 1000 Kelvin. That means the heat engine A is more efficient than heat engine B because both are producing same amount of work, and the source temperature for heat engine A is 600 and heat engine B is 1000. So we have to supply more energy to maintain the source temperature, and the efficiency for heat engine B is less than the heat engine A. So conceptual question answer. So the conceptual question answer is we cannot create nor destroy energy. Can we create or destroy exergy? So we know that the available energy, so energy is equal to available energy and unavailable energy. So energy is the sum of available and unavailable energy. So available energy is also known as exergy. So it is asked that energy cannot be created or destroyed. But can available energy can be destroyed or created? So available energy cannot be created. However, if the process is irreversible, then the value of available energy is reduced. So more the irreversible process is, the lesser the value of available energy. So that the decrease in the available energy is replaced by the term entropy generation. So the destruction or reduction of exergy is directly proportional to the irreversibility of the process. So as the process is more and more irreversible, the value of exergy is keep on decreasing. So the value of exergy cannot be created, however it can be reduced and destroyed as the process more and more becomes irreversible. So in a turbine, what is the source of exergy? So the flow into the turbine is the source of exergy. So the fluid or working fluid that is entering into the turbine provide the source of exergy or available energy. So if the fluid that is exiting the turbine also contains some amount of exergy, then the net amount of exergy will be the sum of exergy that is entering and leaving the system. So let's suppose a fluid with the 100 joule of energy enters the turbine, 40 joule of energy is converted into work and 60 joule of energy is at the exit, and the difference 100 minus 60 will equal to the amount of work done or useful energy. In the pump, what is the source of exergy? So As you know that the pump is a work consuming device, therefore the amount of work that is given or done on the pump, for example, if the shaft work or the reciprocating work is done on the pump, then the amount of energy that is supplied to the pump is utilized to increase the pressure of the working fluid. As the main function of pump is to increase the pressure of the fluid, therefore the amount of energy we are inputting into the pump or introducing or connecting the pump, for example, if we are introducing it with the connecting with it into the electrical energy, so the amount of electrical energy supplied to the pump is utilized to increase the pressure of the working fluid. So in a heat engine, what is the source of exergy? So as you know that heat engine is a work producing device. So a certain amount of heat is entered into the heat engine. Some of it will be converted into work and other will be rejected into the atmosphere. So the amount of energy that is entering into the heat engine is the source of exergy. So if that amount of energy is entering into the that is entering into the heat engine is coming from a source. uh, it may be a finite body or it may be a thermal energy reservoir, so that will act as a source of exergy. The conceptual question answer continues, and the next one is the energy of the ocean is available? So the short answer is no, because the ocean is at uh, atmospheric temperature. So when we are talking about in term of energy in term of thermodynamics, then we are talking about the energy, so the thermal energy that can be converted into work. So we have a work producing device, like if we are talking about the heat engine, then heat engine work on the temperature difference principle. So high temperature heat is entering into the heat engine and some of it is converting into work and other is leaving into the ambient or rejecting into the sink. So as the heat engine require temperature difference, but the ocean cannot provide the temperature difference because it is present at the ambient temperature. However, when you will be studying the renewable energy subject, then you will came to know that there are certain other method to absorb or to convert the ocean energy into useful work. So it may require the wave energy or tidal energy. So certain devices are present that convert that energy into electrical energy and other form of energy as well. However, in a certain portion, in a limited time span, if you can find out a temperature difference within an ocean, then you may utilize a heat engine to convert or extract energy from the ocean. But that will be a very limited case and with a very limited time span. Numerical problem. A heat engine receives heat from a source at 1500 Kelvin at a rate of 700 kilowatt, and it rejects the waste heat to the medium of 320 Kelvin temperature. The measured power output of the heat engine is 320 kilowatt and the environment temperature is 25 degrees centigrade. Now you have to calculate the reversible power, the rate of irreversibility, and second law efficiency of heat engine. So this is the schematic diagram of heat engine. A heat engine is connected to the source of 1500 Kelvin temperature, absorbing 700 kilowatt of energy, producing a 320 kilowatt of work, and rejecting the rest amount of unavailable energy into the sink, that is at a temperature of 320 Kelvin temperature. Part 1, to calculate because this is a reversible power. So for example, to calculate the reversible power, you are assuming the heat engine is a Carnot heat engine. So you will be utilizing the efficiency for Carnot heat engine. So the efficiency of Carnot heat engine is 1 minus T2 over T1, and efficiency is also equal to W over Q. To calculate the W, you will, and then the q is in the denominator on the left hand side, so it will multiply on the right hand side. So W max is equal to q into 1 minus T2 over T1. So T2 and T1 temperatures are known. So T2 is the temperature of sink and T1 is the temperature of source. So Q is the amount of energy that is entering into the heat engine. So 700 Q is equal to 700, T2 is equal to 320 Kelvin, and T1, the source temperature, is 1500 Kelvin. So the maximum work or reversible power, so power has the unit of kilowatt, so maximum work also have the unit of kilowatt. So maximum work or reversible power is equal to 550 kilowatts. So the rate of irreversibility, so irreversibility is represented with the symbol of capital I, that is equal to maximum amount of work that can be done and actual amount of work. So the difference of irreversibility is the difference of maximum work minus actual work. So actual work that is given in the statement, so actual work produced by the heat engine is 320 kilowatt, and in the previous step we have calculated the maximum amount of work. So we have assumed if the Carnot heat engine is placed over uh, replaced by this heat engine, so it will produce 550 watt of work, and actual heat engine produce 320 kilowatt of work. So the rate of irreversibility is I is equal to 230 kilowatts. Now the third question was to calculate the second law efficiency of this heat engine. So as we have derived the relation, and we know that the second law efficiency is the efficiency of actual heat engine divided by the efficiency of Carnot heat engine or reversible heat engine, that is the maximum efficiency. So the efficiency of actual heat engine is W by Q, that is 320 divided by 700, and the efficiency of maximum heat engine is 1 minus TL over TH, that is the formula to calculate the efficiency of Carnot heat engine efficiency. So TL and TH are also known, that is the temperature of sink and source. So 1 minus 320 over 1500 is the efficiency of Carnot heat engine. So when we divide both these efficiencies, so actual efficiency 320 divided by 700 and maximum efficiency, that is 1 minus 320 over 1500, then the second law efficiency came out to be 58%. So that is the last numerical for today. Home assignment for lecture 22. All students are advised to go through example problem of each topic discussed in this lecture. So you are advised to go through example problem as well as the exercise problem as well, uh, regarding the topic that are discussed during this lecture. So you are required to write a handwritten lecture summary report and send it to my email ID arsalan@cietbar.edu.pk. You are also advised to prepare this lecture thoroughly, as you may be asked question answer session. There will be when there will be online video session with you. So that is all for this lecture. Take care. Allah Hafiz.